a second. So if you saw it in practice, symbolically speaking, you would see, hey, for all or for any x, then it would talk about whatever your mathematical sentence is or your logical statement. This is the same thing if you dealt with sets. You'd say something like, for all elements x in your set would be how it would be written there. And that's how you would read it out. Now the existential quantifier, this one here refers to existence, or there exists something, there is something. There is what people will often say, but to be very proper or correct, there exists is the more proper one. The symbol that represents the existential quantifier looks like a capital E but backwards. I'm assuming that these guys that look like capital letters but backwards or upside down, E for exist, A for all, is my guess of where they came from. In terms of use, notice syntactically it's exactly the same as the universal quantifier. You've got there exists some x such that, and then you've got whatever the statement is, your logical statement or your mathematical sentence. Okay? The examples that we'll have will all be dealing with mathematical sentence. Why? Because we're a math class. Now, there's one last thing that you can do with these different types of quantifiers, and it's actually an adjustment on the existential quantifier. In other words, it's one extra thing you can do with your existential quantifier, and some people actually give it a new name called the uniqueness quantifier. That's more of a descriptor than anything else. The two ones that have actual names were those first two, universal and existential. Again, I do not care if you remember these names or not, as long as you can actually use them. So the uniqueness guy looks exactly like an existential quantifier. The existential quantifier, remember, tells you there exists something. That means there's at least one of whatever that something is. The uniqueness quantifier goes one step further. It says not only does it exist, I know how many of them exist. Specifically, there exists exactly one of this, whatever it is you're looking for. Syntactically, it looks exactly the same as the other guys. You'd say there exists exactly one x such that or where your whatever your predicate is happens. So that's all the theory. Let's jump into examples. And before I jump into examples, any questions from you guys? All right, so examples. So the following are going to be a list of different predicates with quantifiers, and what we're going to want to do is we're just going to check to see which one of these guys look like they're true, which one is false. So this is the tie-in between the quantifiers and what we were doing previously with our logical statements. One of the things that you pretty much always want to do when you're dealing with logical statements is you want to find their truth value. Is this statement true? Is this statement false? So how would we see our quantifiers? This would be how you'd see a quantifier in use. So this guy reads as for every integer, which we're going to call x. So remember here, this guy right here, that's the for every or for any or for all. So for all integers x, how would I know to say integers? Because this tells you that your x symbol is coming from the set of integers. So this says for any integer, x squared minus 3x plus 2 has to equal 0. What do you guys think? Does that seem believable? In other words, is that statement always true? Remember, the true, false, the true or false value of a statement means it has to be true in all conditions. So I have answers coming in both for yes and for no. One of those answers is correct. So how would you tell if this is a true statement or if it's a false statement? In order for it to be a true statement, you have to be able to run every single possible integer out there, plug in that integer in for x, and always get back 0. Can you find an example of an integer that you could plug into this equation where the equals isn't correct? Anybody spot an x value that would make that false, in other words? Sure. I really don't want to plug that in, but yeah, if you plugged in x equals 100, you get 100 squared, so what is that? 10,000? 1 into 4 zeros. minus 3 times 100, so minus 300 plus 2, that's not going to give us 0. So this is a false statement because there's at least one integer that makes this equation not true. And in order for this to be a true statement, all integers had to work for that equation. Now, when I typed this up, I didn't use 100. I actually used 0 because I was super lazy. And same thing happens if you plug in 0. You get 2, which is not 0, which is not the 0 you wanted. Now, suppose you take the exact same equation, okay? And the only thing that changes is we change the quantifier from the universal quantifier, the for all, and we change it to the existential quantifier, the there exist. So this one would be read, there exists at least one integer, which we're going to call x, such that x squared minus 3x plus 2 equals 0. This one is not the same as the last one. Here, when we're looking at our equation, all we're trying to find is at least one x. That's an integer that will make this work. So what do you guys think? Do you think we could find at least one integer x that would make that equation true? Yeah. So if you go ahead and pick x equals 1, we could plug in 1. We'll get 1 squared, which is still 1. We have 1 times 3, so 1 minus 3, that's negative 2. Plus 2, that's 0. So yeah, this would be a true statement. And in fact, there's exactly 2 of them that would make this a true statement, either the one that you guys picked or actually 2 would work as well. But most people find the 2 after you start factoring. Now, if this had been one of those quadratic equations where either you factored it and one of these guys turned out to be a fraction, or you didn't factor it and used a quadratic equation, you got only fractions and square roots, that would be when this thing would be false because your roots wouldn't be integers, they'd be fractions or including square roots. Or imaginary numbers, actually, that's a possibility too. Now, same exact equation, but now the quantifier has changed again. So in this case, this is the uniqueness quantifier, which technically is more of a description than a name. So suppose you read off this guy, and it says, there exists exactly one integer that we're going to call x, such that or where x squared minus 3x plus 2 equals 0. What do you guys think? Is that a true statement? Ooh, we've got 1 vote for false, 2 votes for false. Yep, it turns out this is a false statement. And why would you guys say it's a false statement? What's the key piece of information that we already knew that made that predicate C false? Anybody spot it? Yeah, that's the key giveaway. When we came up here in part B, we only needed to find one x value to make this statement with the existential quantifier true. But over to the side, we went ahead and did scratch work and showed how to do it with the arithmetic. Well, really a review. I'm assuming you guys can do all that just fine on your own. But we came and found that there was more than one solution. As soon as you get that second solution, or if you had more solutions, that's when you don't have this uniqueness. Uniqueness means only one. Whereas the general version of the existential quantifier, it doesn't matter if there's 1, 2, 3, 4, we don't care as long as there's at least one. And that's the big difference between these two guys. But the uniqueness quantifier in everything else acts exactly the same way as the existential quantifier. The only thing that's different between these two is the uniqueness quantifier has the one extra condition of exactly one solution, if you will. All right, so last example on this slide, and for this one, I changed up the equation now. So in this particular case, the equation now is x squared minus 2x plus 1 equals 0, but we still have that uniqueness quantifier out front. So if we go ahead and read it out, this would say there's exactly one, or there's a unique integer x, such that x squared minus 2x plus 1 equals 0. So any guesses what we would need to do if we wanted to verify if that was true or false? What would we need to do? Or if you think you have a guess for true or false, that works too. Yeah, so just like with part B, what we'd want to do is we would want to find those answers. We'd want to find these solutions for x, the zeros, the roots, whichever way you want to call it, but we'd want to actually solve for x here. Once we solve for x, if we get an answer for x, we would have this, it exists, but then we'd have to make sure there's exactly one of them. So I'm going to claim that this one actually does turn out to be true, and it's because when we solve for x, the polynomial does factor, but it factors so that the two factors are exactly the same factor, so this x minus 1 squared, and that's what gives you just the single distinct root there, or the single distinct 0. Make sense? Feeling kind of okay so far? But that's the basics of quantifiers. They essentially frame your world, if you will. You have something in math, often some equation or otherwise, and this tells you, all right, we're going to have all of our x's from this equation come from integers, and we're looking at everybody in integers, or down here, we're only looking at some integers for this situation. But seeing no questions come in from you guys, let us look at something else you can do with quantifiers. Okay, it's not really something else, but it's more, you can actually combine multiple quantifiers together. In other words, you can stack them, if you will. Okay? So you can make it so that you have more than 2 quantifiers. So here, I only did a demo with 2 quantifiers, and I did both of the 2 quantifiers. I have the for any, or the universal quantifier, as well as the there exist, or the existential quantifier. You could also flip the order. You could also make both of these guys the universal quantifier, so both of them for all, or both of them the existential quantifier, so both of them are there exist. So you can throw them together in however you want to. But if you look at them just with 2 and 1 of each, here's an example of what that would look like. Okay. So for this one here, again, it's an equation. But this equation has actually been solved for one of the 2 variables. I went ahead here and solved for y, so it actually looks like a function. So how this is read is it says, pick any integer x that you want, then there exists some real number y such that this equation is correct. In other words, y equals 3 times x minus 4 over 1 plus x squared. Now, if we wanted to verify the truth value of this particular guy, what is it that we would need to be looking at? Well, first thing is there's not as much solving like the other guys. It's more of a talking our way through it. So this first part says we have to be able to use any integer we want for x. So pick your favorite integer. Any of them should work, a positive integer, a negative integer, or 0. And then you plug it into this expression on the right-hand side. So you plug any integer in, you multiply by 3, you minus 4 over 1 plus whatever that integer squared. Yeah, so maybe you pick 1. So in that case, you'd have 3 minus 4 over 1 plus 1, and that would be a perfectly fine guy. Now, here's the question for you. If you pick any integer, whatever you want, maybe it's something like 1,000,000, maybe not. Maybe it's something like 5, maybe it's something like 0. Maybe it's something like, oh, I don't know, negative 10. Regardless of what integer you pick when you plug it in, will you always get this expression on the right-hand side to be a real number? What do you guys think? You guys have dealt with functions before. You plug in an integer for all these x's, will you always get a real number? Well, we've got 1 vote. What do the rest of you guys think? So the thing is, knowing about real numbers. So remember what real numbers are. Apparently I accidentally touched something I shouldn't have touched. Just a second. Real numbers are what? They're all the numbers we normally work with. They're fractions, they're decimals, they're integers. The only thing that you can't have is you can't have imaginary numbers, okay? But it is a number that exists. So here, is there any way to get an imaginary number if you started with an integer for x? There's no way to get an imaginary number whatsoever. So the only time that this expression would not be a real number is if you do have a divide by 0, which is exactly what one of you just said. Here at the bottom, put in any integer you want and square it, well, if it's a positive or a negative integer, this will be some value 1 or bigger. If it's 0, it would be 0. So x squared is always 0 or bigger. But 0 plus 1 is 1. So the smallest that this denominator right here could be is 1, which means you're never going to get divided by 0, which means, yes, you actually can plug in any integer you want. Once you plug in any integer you want, the first term will be some integer, and the second term could be an integer, but most likely it's going to be a fraction. And this guy minus some fraction is totally still a real number. In actuality, we actually could have switched out this symbol for real numbers and have put simply rational numbers, which are the set of all your fractions. Okay? So this one actually does work. What I would recommend if you have a question like this on your own that you need to work through is actually pick a bunch of test cases. So like in this scenario, let me get my writing instrument out. In this scenario, I would actually do some test cases. No lie, by this point in my life, I actually would do them in my head. But I'm not assuming that you guys can do everything in your head yet just because you haven't worked with the material as much. I would actually get a couple of test cases, and I typically would recommend at least 2 negatives. Always pick 0, because 0 has a tendency to be weird. And then pick at least 2, and people most of the time recommend 3, so 2 to 3 negative numbers and positive numbers. So these guys are all some test cases for integers. You plug it in, you check to see if y is a real number in each case, and what you would find is it would be. The only thing that's a holdup is making sure you remember what a real number is. Huh? So any questions before we move on to negating quantifiers? And in terms of the order that you read it, notice what I did. The first one here, we dealt with first, and then we double-checked that the next one actually worked. Okay? So in terms of this guy here, where you have the 2 different quantifiers, the order in which you write them down will actually matter because there's a conditional relationship there. All right. I am not seeing any questions come in from you guys, so let us look at negating quantifiers. And remember, negating is simply taking the negative of, or in terms of logical statements, this is where we put that negation symbol out front. I was trying to use a different word, but it's really descriptive at this point. So it turns out if you have the universal quantifier, so this one here, the for all, and then whatever your predicate is, whatever your logical statement is, and you want to negate this entire compound statement, or really quantified statement, if you will. There's 2 things that happen. One thing is you need to actually negate whatever the logical statement was. In our case, we've had mathematical equations, so we would negate whatever the mathematical equation was. But the other thing you do is you actually flip who the quantifier is. So if it started off with a for all, a universal quantifier, it would totally flip over to an existential quantifier, and the other way it works as well. If you started with an existential quantifier, it would flip to the universal quantifier. So they reverse. Please note the uniqueness quantifier is a specific type of existential quantifier. So if you have a there exists exactly 1, or there's a unique x here, that would still turn into a for all over here. So let us look at some examples. The first example that I've got for us is somebody we looked at just a second ago. So this guy is for all x's that are integers, x squared minus 3x plus 2 equals 0. And we already know that this particular statement was what? We found previously that it was a false statement because not all x's work. Which means if we negate this statement, what has to happen in terms of the truth value? The negation of this statement must be what? True or false? What do you guys think? Yeah, it would have to be true. So one way to double check that you've negated your statement correctly, if you already know the truth value of the original statement, you would then double check that the truth value of the negated statement is the opposite. Now, in practice, that's not normally what happens. Normally, you don't know the truth value of one of them. You negate it, and you're able to find the truth value of the negation, and then use that information to find the truth value of the original. So here's what I'm going to claim the negation is. First thing we're going to do is the for any part. We're going to swap it to the other quantifier. So for any turns into there exist. So instead of everybody has to work, at least one of them has to work. Okay? You keep the equation exactly the same, except when you negate an equation or a mathematical statement, specifically an equation, you take the equals and turn it into a not equals. Okay? So if we then go ahead and look at this guy, remember it's supposed to now be true. Can you find an x where when you plug it into x squared minus 3x plus 2, where this expression doesn't equal 0? Can we find an x there that makes that not equals, not equation to be true? And the answer is yes. And yeah, you could totally pick x equals 0. We could also pick the same x that we used before, which I believe was x equals 100. We could also pick pretty much anything that's not 1 or 2. So that one totally becomes true, just like what we said. Now suppose we have this other guy. Now this other guy is this. So this was also somebody that we looked at before. And we said previously that this guy had a truth value of true. So when we negate it, it better have a truth value of false. So that's what we're going to check. Okay? So when we negate this one, their exist quantifier will turn into the for all quantifier, and the equation, the equals part, well, the opposite of equals is not equals. Okay? Now, if we look at this guy, what do you guys think? That now in black type, does that new or negated statement look like it is false, which is what we're hoping happens, logically speaking? What do you guys think? Is that false? In other words, how would you tell if it's false? You're able to find at least one integer where the equals is actually true. And we actually did this one before. So this one here says that this equation is supposed to never be true, but we know that's not right because we were able to take this equation and solve for x previously. So just pulling the two guys that we had previously, either 1 or 2, or if you want, you can look at both of them, but we only need one of them. If you plug either x equals 1 or 2 into here, you will get an equals instead of a not equals. So that means the statement in black here has to be false because the equation actually can be solved for x, and the solution for x, at least one, in this case actually both of them, are integers. Hopefully that makes a little bit of sense. So questions about negating quantifiers. Sometimes when you get into actually dealing with quantifiers, it feels like there's more pieces and parts going on, but quite frankly, everything we just talked about, that's literally it in terms of quantifiers. Okay? In the homework for this section, there is a question or two. I think it's just a multi-part question in your book that plays around with some of the different ways that you can see quantifiers, and I think he tries to trick you or something, but it's really more of a way of making sure that you can see all the different ways that quantifiers can be put together. Don't overthink it. It's literally doing this exact same thing that we just did together. All right. So now we're going to come back to dealing with truth tables. There are a bunch of other operations that can have truth tables, but we're only really going to look at one more, and that is a type of conditional statement, which is the implication statement. Just like when we had previously where we were dealing with ands and ors and nots, I believe those were the only three we got to last time, and, or, and not. The implication or the conditional statement deals with originally two simple statements or two sort of base case statements and then combines them together to get a compound statement. So here we'll go ahead and let P and Q both capitalize to indicate statements, although many books do lowercase as well. The implication would be the if P then Q. And a lot of times people just write that out, but symbolically it is P implies Q is one of the ways to read this. You can also just read it as if P then Q, but notice the arrow here is 2 lines. It's not a double-headed arrow, but it's like a double-lined arrow. And that's because in math, if you have a single line for your arrow, it actually means something else. If you've had calculus, it means you're taking a limit. So in terms of naming conventions for the implication statement or the conditional statement, there are some naming conventions on the P and the Q statements, and that's because order matters here. Notice the arrow has a direction. There's totally a reason this thing is an arrow. It says you start here at P, then you have to get over here at Q. Okay? Well, the starting point, this if part of the statement, is called a couple things. A lot of people just call it the if part of the statement. It's also known as the hypothesis, is the official name for it, and to be a little bit, and the other official name for it is something called the antecedent. I do not care which of those 3 naming conventions you use. I believe your book uses hypothesis, and I have a tendency, just to make sure everybody's on the same page if you didn't remember one of these words, to just call it the if part of the statement. Now, the then part of the statement also has 2 official names. One is called the conclusion, and the other way of calling it is the consequent. I believe your book uses the word conclusion, and I'll be honest, I typically call it the conclusion as well. Now, this guy, just like with the ands and the or statements we had yesterday, does have a truth table associated with it. And in this setting right here, same as with the ands and the ors, since we have 2 statements, we have a grand total of 4 rows in the truth table because we need to get all combinations of true and false based off of your P and your Q statements. So P could be true, but when statement P is true, Q could be either true or false. When statement P is false, Q could be either true or false. Now, of all the truth tables, the implication truth table has a tendency to mess with people's heads the most. So here's how to read this. If you start off in a true location and you do all of the work correctly, so think of this as like maybe something that we'll do in this class. You're solving a math problem. P is like the start or the question that you're given. Q is like the answer you're going to give back. And the implication is saying, hey, did we actually do all the work correctly? So in this particular situation, what happens? Here, if you start from a true place, this is like you copied down the question correctly, and then you got to the correct answer. Well, that implies that you probably did it correctly. Now, the second row says you copied the question down correctly, but you got the wrong answer when you worked the problem. Well, what does that tell you about your work? This tells you that somewhere you made a mistake. Now, this one down here says, hey, or I guess really both of these 2 rows down here. I can actually do these 2 rows together. This is like you copied the question down wrong. So you started in the wrong location. You started in a place that wasn't true. Then your answer, maybe your answer actually was the answer you were supposed to get, but this says that when you did all of the work, maybe you did all the work correctly and the question you wrote down actually did have the same answer that you were supposed to get from the other question you were really supposed to work. Down here it says, hey, the answer that you got was not the correct answer of the question you were really supposed to work. But here, the assumption is that, yeah, you actually did all the correct work logically, all of the correct steps. You just got the wrong answer because you started with the wrong question. Okay? Now, true fact, when you're working things, especially in math and other places too, you really don't want to start at a false statement. Okay? So these guys here, while true and definitely are going to be things that we will use, in actuality, it is the top 2 rows that we're really going to be focused on. In other words, you start at a true location, and then the implication is double checking that all of the reasoning you used to start from a true location really got you to a true location or didn't. If you got to a correct conclusion, your logic was correct. If you got to a false conclusion from starting at a true statement, that means your logic screwed up somewhere. So that's sort of the idea of what's going on with these top two rows. These bottom two are really more for completeness. Now, I've got an example prepped up that hopefully tries to illustrate this, and it's in terms of like a math statement. Okay? So this one here says, suppose you're trying to check the validity or the truth value of the statement that starts with, if x and y are even integers, then the sum x plus y is also an even integer. And I included the word even integer, but technically speaking, the definition of even says you have to be an integer. So in this particular case, your if part of your statement or your hypothesis would be the part before the then. In other words, the part attached to the if in the actual sentence, so before the comma. So y and x are even. And the conclusion is we want the sum to also be even. So I'm going to put together a chart, and this chart is going to mimic the truth table of the implications, except, well, it's got a one extra row. So there's possibilities. If you're looking at two numbers and you're checking to see if they're both even, well, it turns out they could both be even. Or if you were just grabbing random integers, one of them could be even and one of them could be odd, or they could both be odd. Notice here, though, when you're looking at these guys, and let me go ahead and classify them. If you're looking at those bottom three rows, those bottom three rows are all where you started off with your hypothesis being false. Okay? Up here on the top two rows, this is where both of the integers are even. This is where our hypothesis or if statement is true. Then, here's your conclusion. This is where you actually calculate, hey, is the sum even? If you calculate that the sum of two even numbers is still even, that means you got a value true here. If you calculate that that sum was false, or that sum here was odd, the truth value here would then be false. Now notice, think about what you've done in the past. You guys have added integers together. If you add two even integers together, do you think that this thing should be even? What do you guys think? Should that conclusion right there be even? Well, this is actually something we'll go over in a little bit to show what will happen. But think of an example of, say, 2 and 4. If you add 2 and 4 together, what are you going to get? You're going to get 6. Is 6 even? And it turns out, and we'll actually prove this later on, but it turns out if you have two even numbers and you add them together, that sum actually will always be even. So getting that the sum is even would be when the statement here is true. Getting that the sum is odd would be this statement here is false. Now, what does this mean? If you actually got the sum of two even numbers is even, that will give you a truth value of true for the entire statement. If you get that the sum of two even numbers is odd, the truth value of the entire statement is false. I'm going to go ahead and include in here the conclusion. This one here is if you got even. This one here is if you got odd. Okay. Now, when we go down to the last three rows, we'll do the same thing. So the next two rows are you have one even integer and one odd integer. So in terms of what we were supposed to start with, we're starting at the wrong place. But now let's see what actually happens. If you add an odd and even integer together, anybody have a guess on whether it's even or odd? It'd be like adding 2 and 5 together. It should be odd. And that is a perfectly fine conclusion to get. In fact, that is the correct conclusion to get when you're getting even plus odd should be odd. That means the actual implication, the overarching work that we just did was all correct. But that is not at all what this original statement Q said. The original statement Q said that sum was even, not odd. Okay? So that's where this false bit comes into play. Now, last statement right here is what happens if you actually picked two odd integers. So maybe you picked 3 and 5. Okay? Well, we're starting from a wrong place. The if statement told you you weren't supposed to start there. But what happens if you add two odd integers together? What do you think you get, even or odd for the sum of two odd integers? And if it helps, add something like 3 and 5 together. So this one here should give you back an even answer. It does turn out, if you add two odd numbers together, it should always be an even number. And that actually is the same answer as what we were trying to get in our conclusion. Now notice, we started in a spot that was completely not what we were supposed to. So, well, technically our conclusion was true, but it was only coincidence because our starting place was completely false. Now, notice these last three guys, we did all of the actual math correctly, and that corresponds to the truth value of true on the overarching implication. The only place where your implication is going to be false is if you started in a true location. So your statement that you started with was true, but somehow you ended up at a statement that was a false statement. And what that means is your logic or reasoning along the way screwed up somewhere. Okay. So that's the idea behind the truth table. But at the end of the day, in terms of how we'll use it, you basically just need to be able to use this truth table even if you forget all of those reasonings behind the scenes. So let us look at some examples. So example that I've got for us is the following. Suppose you have the following statement. It says, if 4 is an integer, then 1/4 is also an integer. What do you guys think? Does that seem like it is a true statement or a false statement? Don't overthink it. Do you believe that statement? All right, we've got one vote for false. Anybody else have a guess? Think he's right? All right, well, let's check it out. Apparently I am accidentally touching the wrong thing there. All right, so what do we have here? We have the if part of the statement, or the hypothesis part of this conditional statement, says 4 is an integer. Is 4 actually an integer? Yeah, yeah. I mean, I don't know how to describe it more than yes. Now, then we have the then part of the statement, and it says 1/4 is an integer. 1/4? What do you guys think? Is 1/4 an integer? Yeah, 1/4 is definitely not an integer. So this would be a situation where you started in a true place, 4 being an integer, and then somebody told you something completely ridiculously false and said 1/4 also has to be an integer. And you're like, wait, what? So this would be a situation where you would have a false implication statement. Okay? But that's one of the ways to tell the validity of your implication statement is you check, did I start with a true location? Then I need to check if I'm also got to a true location. Now, suppose we have something that's actually really similar here. This one, the if part, also says 4 is an integer, but it gives you a little extra information. It says not just 4 is an integer, it also tells you that we're going to call for x in the future. Okay? Well, calling for x, there's no way to tell right now if that's good or not. That's really just a naming convention. So this first part of this statement, again, says 4 is an integer. Now, the then part of this statement says x squared minus 1 is also an integer, and that's why we need the naming convention up here. So what do you think? Is this last part, is this then part of this conditional statement, is this conclusion of the statement a true statement or a false statement? In other words, if x is 4, do we think x squared minus 1 is going to be an integer? Yeah, it looks pretty true to me as well. I mean, worst case scenario, just plug it in. So we'll have 4 squared, which is 16 minus 1, so that's 15. Is 15 an integer? Yep. So this is one of those situations where you have true implies true, and this means that the entirety of the entire truth value of the whole implication would still be true. So then we get a third example, and I've got 4 examples here. So third example says, suppose square root of 2 can be written in the form of a over b, where it wasn't written down because I ran out of space. The assumption here is that your a over b are actually integers. The assumption here is that a and b are both integers. And because it's a fraction and we would love for it to be defined because square root 2 is defined, we'll go ahead and assume that b is not 0. But in terms of format, it's just saying you can write square root 2 as a fraction. So that's the hypothesis, the if part of the statement. The then part of the statement of the conclusion says square root of 2 must be a rational number, or is a rational number. So what do you guys think? Does that entire sentence, that conditional sentence, seem like it is believable or not? Not going to lie, this is a trick question a little bit. So first, my mouth is not fully functional today apparently. There's 2 big things you have to know. One is what in the world is the definition of a rational number? The other thing is you got to know something about a square root of 2. Okay? The first thing is, anybody remember what the definition of a rational number is? We've talked about it a little bit in our course, but we haven't really done. Ooh, that actually is where the name comes from. It's not where everybody can see, but somebody sent in that rational numbers are dealing with ratios, and that actually is where the naming convention comes from, is that they are numbers that can be written as ratios. Now, what does that mean in layman's terms? Anybody have a guess? It means we're dealing with what type of numbers? Don't overthink it. Rational numbers are also the numbers indicated by that capital letter Q. Ooh, I'm going to combine the last 2 answers that came in. In layman's terms, rational numbers are any number that can be written as a fraction. So this includes all counting numbers, this includes all integers, it includes all numbers that can properly be written as fractions. It does not include all real numbers, and it does not include all imaginary numbers. Actually, it includes no imaginary numbers. But rational numbers are defined as anybody who can be written as a fraction is one of the ways that we typically define them. Now, that being said, if we actually had this first part, notice this first part, this if part of the statement says square root 2 can be written as, and it gives a form. What does that form look like to you guys? Don't overthink it. That looks like a what? Totally looks like a fraction, right? So this first one says square root 2 can be written as a fraction. Now, if square root 2 could be written as a fraction, is it okay to call it a rational number? What do you guys think? Yes or no? If we can write square root 2 as a fraction, can we then call it a rational number? Yeah, because that would just be using the definition of a rational number. Now, here's why it's a trick question. Anybody know if you actually can write square root 2 as a fraction? Ooh, I phrased that question wrong. Can we rewrite square root 2 as a fraction, where you only have an integer over an integer? Oh, okay, yes, I was not precise with what I asked. That is true. Well, you have to have a negative in that exponent at the end. Can you write this as a fraction where on the top you only have an integer, and on the bottom of the fraction you only have an integer? So no exponents allowed other than a 1. everything is silent. It turns out square root 2 is not a rational number. It turns out there's no integer a, there's no integer b that you could ever find. And depending on time, we'll actually go over this example. It would probably be Tuesday that will make this work. This actually turns out to be the case where, nope, you can't ever write square root 2 as a fraction, as what we consider an actual fraction, which is integer over integer. And that also means that square root 2 is not rational. But the implication is still true, because if square root 2 could be written as a fraction, then it would totally be called a rational number. But unfortunately, neither of those two individual simple statements are true on their own. But this one is probably one of the more trickier questions, just because you're starting with, or you're dealing with a bunch of different very false information. But the way that they're written, the way that they're tied together, actually does give you a true logical statement. It's just not very useful because square root of 2 is not a rational number. Oh, I guess I did need that. So, last example on this page says, let n be an integer. Now, this guy here is actually before the conditional statement. It's just telling you how we're going to use the symbol n. And this often happens when you're writing the statements out with sentences, is you need to tell your reader what your symbols are going to be dealing with. This is almost like, this is basically like writing quantifiers out with words. Okay? Then the statement here goes as follows. It says, then n squared is going to be an odd integer if and only if n is an odd integer. Now, this one is written a little bit differently. At this point in your mathematical career, you may or may not have seen if and only ifs before. Sometimes you see them a lot in high school and various other places, and sometimes people don't. Okay? If and only if statements are called biconditional statements, and what that means is you actually have two if-then statements together. Okay? You actually have, and we'll do the formal definition of this in just a second, you actually have here, if n squared is odd, then n is odd, but you also have, if n is odd, then n squared is odd. And sorry, I did not push hard enough on that S to make it show up. Okay. That's the biconditional or if and only if part. Now, anybody have a guess on whether that statement is true or false? So what I would recommend when you're checking out true and false things is doing some examples. I mention that because we've got guesses on both sides of the spectrum here. So think about squared numbers, and it's definitely easier to see it from n here. So maybe you pick 3. If you square 3, and why did I pick 3? Because 3 is odd. If I square 3, we get 9. Is 9 odd? Yeah. So that's an illustration of this guy. Now, is it a proof? Is it verifying that this works in every time you have an odd number? Absolutely not. But we'll look at this example a little bit later on. Okay? Now, what happens if you take a square number and it starts off being odd? Maybe you pick 25. Now, if you pick 25, then if we look at the square root of 25, what would be the square root of 25? And is 5 an odd number? Yeah. So now, those were only one illustration going in either direction of this biconditional statement. That is not enough to give a definite conclusion that you actually have, that the statement is true in all situations. We'd have to do more than just those little examples. But it gives you an idea. It gives you an idea and says, hey, you know what? I've seen square numbers that were odd before, and their square roots seem to always be odd, or often were odd. And every time I've squared an odd number, its square was odd, at least as much as I can remember. So that's one of those things where it gives you a clue that says, hey, maybe this statement actually is true. Now, if you're still doubting it, that's when you try to find a case where it fails. But we'll actually go over this example more later on. It turns out this example actually is a true statement, and we'll go over how you could show it's a true statement in just a little bit. Depending on how far we get, we'll either get to this one at the very tail end of today or towards the beginning on Tuesday. And I keep mentioning Tuesday as the next day that we would see each other because, any guesses why? Because normally we'd see each other on Monday, but Monday's a holiday. So Monday's Memorial Day, it's university holiday, everybody's shut down. So I'm not planning on meeting or anything. Following the same schedule as if we were actually coming to campus in person. I like that. If I always canceled Monday classes, I don't think anybody would complain unless it was a Monday-Wednesday class. But yeah, it's because it's a holiday. It's actually one of the reasons, if you've looked at the schedule for our summer session, we're supposed to be 5 weeks. We have all of the days of the 5 weeks, except we have one last Monday on the 6th week. That's because we have the holiday next week. Okay? But yeah, no class on Monday. I don't have anything due on Monday either. Everything that would normally be due on our Mondays, because homework is normally due on Mondays, are going to be due on Tuesday. Okay, so you got the extra day there. That's also why I haven't been completely freaking out that some of those assignments aren't posted yet, although they should be later today. All right, so the next thing is this example right here. I see a couple of you have already found it. I'm going to go ahead and share with you where it is over on the Poll Everywhere site too, because that actually gives you the URL up here if you don't have it saved somewhere. So take a second, see if you have a guess on whether this implication is true or false. So it says the following thing: if an integer is both a perfect square and a prime number, then it must be a negative number. And actually, oh, I see about half of you have already answered. I was about to say I could throw you into groups so you to talk about it, but if half of you have already answered, I'll just let you guys pick a guess there, and then we'll talk about it together. All right, so let us see what you guys thought. I'm hoping it's not 50-50. Ooh. Okay. So, do you guys want to see the right answer? You guys are going to love this. Now, the question is, why in the world would this thing actually be true? Okay? So I'm going to go ahead and hide the screen, and we'll put scratch work and stuff on the one I can actually write on. All right. So it turns out that this guy actually is a true statement. And before you're like, wait a second, everything I thought I knew about sentences is false, why is it a true statement? So remember what we did when we're dealing with implications. If you are true implies true, that means the entire truth value is true. If you have a true statement and it implies false, that is, well, incorrect because somewhere your logic went stupid wrong. But if you have false implies true, that is also considered a true statement. And if you have false implies a false statement, that is also considered a true statement. Notice the last one right here. We had an example of that before with this square root 2 sentence. Okay. So let's evaluate each of these two guys individually. The first guy right up here says you have an integer that's both a perfect square and a prime. So this guy is your statement P. Okay. And then if we look at the other part, the is negative part, that would be the then part of the statement, the conclusion or the Q part of the statement. So I'll go ahead and put Q down here. Okay. So if we look just at that if part of the statement, the hypothesis part of the statement, could we ever find an integer that is both a perfect square and a prime number? What do you guys think? Could we ever find an integer that's both a perfect square and a prime number? So let's list them out. Okay. Whoops. Do not want to do that. So if we have perfect squares are integers of the form n squared. So you've got ones like 0 squared, you've got 1 squared, you've got 2 squared. What are a couple more? After I try to establish the pattern for you. In other words, what would be the next, say, two numbers that are perfect squares? Yep, the next one would be 9. What would be, and 16, perfect. I'll go ahead and put 25 on the end there just because I like 25. I don't know why, I just do. It's probably because I did something with 25s and quarters when I was in elementary school and stuck around. Anyway, now if we look at prime numbers, anybody remember the definition of a prime number? And this one here is the key part of this question. So I'll start writing out some of the small primes while you guys are thinking about what the definition is. So 2 is a prime. 2 is actually the only even prime, excuse me. 3, 5, 7, 11, 13, 17, 19, 23. Try to match it up there to the 25. Correct. So a prime number is defined as a number where there's only two factors, well, two positive factors. So the two factors of a prime number are 1 and itself, or the two positive, because you can actually have the negative versions in there, but we're ignoring negatives for now. Okay. So when you look at these guys, notice primes have those two factors, 1 in itself, but perfect squares have how many factors? Anybody have a guess in terms of our perfect squares up here? These guys will always, 1 in itself will divide in as factors, but perfect squares also have what? At least starting with 4 and above. So what we're trying to figure out here is if the only factors of our perfect square, or if any perfect square has only the factors 1 and itself. So we're trying to figure out if any perfect square could also be a prime number. So what do you guys think? Is it possible that a perfect square could also be a prime number? Correct. So it turns out that a perfect square and a prime number are going to have exactly no overlap whatsoever. And the reason for that is perfect squares always have at least 3 factors, starting once you get at 4 and above. Okay. So for these guys right here, at 4, what happens? The factors are going to be 1 and 4. That's the same as a prime. But you're also going to have the 2 from the 2 squared. Now, when you go further up at 16, they're going to have more than 3 factors. So a perfect square always has at least 3 factors once you're at 4 or above. Now, 0 actually has infinitely many factors because it's 0 and whatever other integer you ever want to use. Okay? Now, 1 is special. 1 actually only has 1 positive factor. 1 is also not prime. So note 1. Wow, I wrote that completely wrong. Not prime is 1. Now, all of that gets us to the following. All of that gets us to the conclusion that there is no integer that is both a perfect square, because perfect squares have at least 3 factors once you're 4 and above, and prime. So that tells us that P, right up here, this guy, has a truth value of false, which when you look in our truth table, means we're in one of those 2 cases. Now, do we even need to evaluate what the truth value is for our then statement, our Q statement? And the answer is no. Besides the reason of I don't even know how to begin to evaluate that part after the word then, we know that as soon as we've established the if part of our statement is false, regardless of whether the second half is true or false, the truth value of the entire conditional statement itself has to actually be true. So this is one of those ridiculously stupid cases where if you start off in a false place, we say that the implication itself is a true implication. So this was totally a trick question, just to show you some of the extremes. So hopefully that made a little bit of sense. Questions, a little bit of sense. At least could follow it when somebody else did it. I'm going to assume. Awesome. All right, so next thing is to talk about types of conditional statements. And this is going to be really useful for us. Based on the time it currently is, it'll be really useful for us next week when we start using it. Okay? So there's a couple types of, let's actually make these fly in so you don't see them all at once. That way you can see where I'm talking at this time. All right. So the first thing is something called our biconditional statement. We talked about that right before we went and looked at this poll everywhere question. Biconditional statements are also called equivalent statements. They're also called if and only if statements. And you will typically see or often see, even in typed work, IFF. Right? So if you've ever seen IFF, this is totally the biconditional statement. In terms of symbols, the symbolic notation looks almost identical to the if-then statement. The only difference is you have the double-headed arrow here. Okay? In terms of what it actually logically means, it is the biconditional statement is the same as having 2 if-then statements. And this is what we wrote out right before the poll everywhere question. If P, then Q. And you also have to have if Q, then P. So logically, you have to have both of those 2 guys working. Notice here when you're saying that 2 logical statements are the same, you actually don't use an equal symbol. You use a symbol that looks like an equal symbol except there's an extra line. No, that wasn't a typo. This is actually what you do with logical statements, and that's because these 2 things aren't equal. This means that their truth values are the same. So it's a very subtle distinction, but it's what we do with logical statements. We also have a truth value associated to this guy, and this is why the biconditional statement is also known as an equivalent statement. Notice here, if you have true, if and only if true, that's the same as every time we had the if-then statements. But notice here, if you have true, then false, well, we knew before it was false, so we're good there. But here you have false, then true. That would have been true here, but when we reverse the arrow, true, then false, that's now a false statement, so the whole thing becomes false. Lastly, we have false implies true, false implies false, and false implies false. So that means the same as in our previous truth table with the if-then statements, you'll get back a true value. Please notice here, you're going to get true in exactly 2 places within biconditional statement. The only time that you're going to get true for the entire conditional statement is when you have both of the 2 components to have the same truth value. That's why it's called equivalence relation as well, or equivalent statement, and that's because it's saying, hey, these 2 things are logically equivalent to each other or logically equal to each other. In other words, they have the same truth value. Now, that was probably what we needed before the example we had with a biconditional statement. If we look then at conditional statements in general, they can also be classified. Okay? So the first one is what we've talked about already pretty much most of today, which is the implication statement. If P then Q, that's the standard. Well, it turns out you can rewrite your implication statement. Suppose you take the exact same hypothesis and conclusion, but now you flip the arrow. So you swapped who's the if statement, who's the then statement. This would then be called the converse of the original statement. Converse here is just saying that you've flipped the implication symbol. The next thing is called the inverse, and the inverse statement looks exactly like the original implication, except you negated the 2 statements. The actual arrow, the implication symbol, stays the same, but the 2 individual statements themselves are negated. I would normally say the last one, but we're going to have the biconditional statement come in there at the end as well. But the 4th one down is known as the contrapositive. And the contrapositive is where you do both of the 2 things you did with the converse and the inverse. You negate both of your statements, and you flip the implication symbol. Now, we're actually not going to write it out, but here is how you use these guys or why they're important. The implication and its contrapositive are logically equivalent. That means if you grabbed your implication statement and you knew it was a true statement, well, the contrapositive would also be a true statement. Same deal with the converse and the inverse. Notice the inverse is the contrapositive statement of the converse, as you flip the order of the P and the Q and you've negated both of them. So those 2 also have exactly the same truth value. Here's the fun part. The implication and the converse rarely have the same truth value. Sometimes there's overlap. So if you were making a truth table and you had trues and falses come up, sometimes there's overlap in that sense, but there's no correlation really here in terms of if this one's true, then the other one will be false, or if this one's true, then the other one's guaranteed to be true. There's not. The only relationship between these 2 guys is the fact that you're using the same simple statements to build them. Now, the biconditional statement is when there is some sort of relationship between your implication and your converse. The biconditional statement is when your converse and your implication are both true statements. Or at least that's when we typically like to use them. So that would be the terminology. For us, we're mainly going to be dealing with using the contrapositive to make our life easier. And we'll also have statements that are biconditional. So those 2 last ones are the big ones that we'll see in our class. All right, so let us look at creating a truth table with the implication symbol. Since we haven't done that yet, we've just looked at a bunch of different examples. And then we'll look at the relations and properties dealing with our logical operators. And at that point, we're going to be close to the end of time. Hopefully, we'll have enough time for me to give you a preview of what we'll talk about next week, which is how we start using all of this logic stuff in math. Okay? So our question here, or our thing that we want to do here, is we would like to create a truth table for this compound statement. So the thing that's different about this compound statement than what we did yesterday is 100% just the implication symbols. Okay? So we still have the nots, we still have an and right here, but now we've got 2 implication symbols. Don't overthink it. And this, wow, I did not mean for that to come up all at once. So for this one here, one of the things to do, and let me actually just, it's going to be awkward when I try to get to the next slide. We'll deal with it. So when we deal with this guy here, what will happen is, notice there are only 2 statements, the P and the Q statement. So when we try to put this truth table together, we'll have our P, we'll have our Q. Then we say, all right, well, P could be a true statement, And then Q could also be a true statement, but wait, Q could also be a false statement. But then P could be a false statement, and Q could be true, but Q could also be false. So we'll have our 4 rows. And I'm going to go ahead and put lines here just so my hand doesn't weave too much when we write in the next work. When we then look at this expression, remember order of operations hold, so we start looking at the things that we need to worry about. In this particular case, I might do not Q first. Now, if we want to write out everything, the truth values for all the different possibilities here of not Q, what should we be focused on when we want to write down or fill in these truth values right here? Any guesses? What's the strategy, in other words, to fill in that third column? Yeah, so what we're going to do here is we'll go ahead and take all the true, false possibilities from the Q column and we'll flip them. So T, true here, will turn into false. And that'll happen in 2 places. And the false here is going to turn into, then we'll flip it, it'll now be true. Now, I went ahead and while we were thinking about that, prepped up the next part in terms of order of operations, which would be P implies Q. And remember, for P implies Q, one of the ways that I remember it is the only time that this guy is going to give us a false value is if true implies false. So we go back here to our P's and our Q's. We only need to look at the true rows. When does true imply false? Well, true implies true. That's no worries. True implies false. Whoops, there's the true implies false, so we'll get a false reading. And if we start with a false, it doesn't matter what we end with because both of those are tagged as true. Now, next thing in terms of order of operations is everything inside the big set of parentheses. So this is where we're going to take our not Q and those results with P implies Q. And remember the deal with and. The only way you're going to get true with and is if both pieces are true. So that means here we've got false and true, true and false, false and true. In all 3 of these situations, we have at least one false. So that means in terms of and, we have to have the truth value to be false. But at the bottom, we have true and true, so that gives you true at the bottom. Now, any guesses what the next column should be? In other words, what should we title the next column? According to order of operations, what would we need to figure out next? You got it. So we need to figure out not P next. Now, the nice thing about anytime you want to do not something or a negation is we're just going to flip the trues and the falses from whatever we negated. So make sure you have that thing without the negation symbol somewhere previously in your chart. So here we've got true, true, false, false, which means this guy is just flip them all. So we'll have false, false, true, true. Now, at this point, we have everything we need to do the final guy. So this would be not Q and P implies Q implies not P. And the only thing that makes me a little bit unhappy is the fact oh, no, we are perfect. Excellent. Never mind. Ignore what I was about to say. All right, so in terms of our implication, this would be the if part. This would be the then part. So remember with implication what happens. It's only going to be false if you have a true implies false. Do we have any true implies falses here? We do not. So if we don't have any true implies falses, that means all of these guys are going to be what truth value? Yeah, they will. All of these guys are actually going to be truth value of true. I think this is the first time we've dealt with it where we actually got the same truth value for every single possibility. So what that tells you here is regardless of who your simple statements are, P and Q, regardless of what simple statements you actually plug in there, this statement right here will always be true. And there is a special name for that. And I'm going to go and get rid of the writing we just had and throw in the typed in chart because it didn't fly in. The special name for that is something called a tautology. A tautology is highly, highly, highly desirable because it tells you what the truth value is of the entire statement. Now, we mentioned this a little bit last time, so let me go ahead and put in the other names. If you actually got a statement where in the truth value, all of these last guys came out to be false, this is called either an absurdity or a contradiction. Your book calls it a contradiction, but I have to admit I rather like the absurdity word too. It just makes me smile. And then the last thing that can happen in your truth table is something called a conditional statement, and this is where your truth table gives you back sometimes trues and sometimes false. But what we're really going to want to have happen is this tautology. Okay? But in terms of naming conventions, these are the buzzwords that tell you what happened in your truth table, even if you didn't write out the truth table. Okay? Maybe somebody else did. All right, so that's this example. Next thing I got for us is the properties of our logical operators. And this is where these properties are extraordinarily useful if you're not going to be using a truth table and you need to rewrite your logical sentences. Okay? So the first thing is really how you can rewrite implication symbols. The second line right here says implication is logically equivalent to the contrapositive. We already talked about that. The first one, though, is if you never actually want to remember the truth table for the implication symbol, you actually don't have to, because it turns out there's a way to rewrite implication with just an or symbol and a not. So if you don't like the implication truth table, that's okay. Every time you see an implication, just replace it with that expression of not the if statement or the then statement. Okay. Biconditional statement, we have this one already, so I just collected everything we talked about previously. If you want to negate the implication symbol, this one here, I went ahead and negated the implication symbol as written in terms of the or and the not. So what happens here is it's actually a De Morgan's law. You would negate the P, you'd negate the Q, and the symbol that's currently an or flips to an and. It's actually De Morgan's law for logical operators. Okay. If you want to negate the biconditional statement, you would do the same operation on each of the two implications. So you negate if P then Q, get the same as what we just had. You negate if P then Q, get this guy. And then there was originally an and between them. That and turns into an or. This is like a double De Morgan's law type thing. Okay. Now, that's the sort of general stuff. We also have some properties that are extraordinarily similar to sets. In fact, they look almost identical to set properties. If you say P and Q, that's exactly logically equivalent to Q and P. Same deal with or. In other words, the order in which you write the sentences doesn't matter. Turns out they're also associative. Again, I don't care if you remember these names, commutative or associative, but this is how these logical operators work. Here, if you need to and together a bunch of different mathematical statements or just logical statements, it turns out technically the and operator as well as the or operator are binary operators, so you have to do them in pairs. In reality, you can actually do them all at once, but it's a little bit more tricky than with sets. There's also a distributive property. If you say P, or, Q, and R, you can actually distribute the P through. Same deal if the logical operators were flip-flopped. I'm not actually going to ask you guys to use too many of these properties. This is more of a for your reference. If you have P and P, same as P. P or P, it's the same as P. This is a nice way to sort of simplify your logical sentence. And in terms of negation, if you have two nots, it's back to the original. And if we actually use this one up at the top. If you negate an or statement, the negatives or the negations go on each simple statement. The or flips to an and the reverse here for if you had started with an and statement. Again, those guys are exactly the same as our De Morgan's laws. Whoops. If you want to use these, totally fine. Just watch out. Some of your questions in the future will say stuff about, hey, what's the truth value of this statement? If you want to use these then, that's totally fine. But if your questions say things like, hey, please write out the truth table, in that case, while you can use these, the goal of the question is actually to make sure that you can write out the truth table correctly. Okay? just as an FYI. All right, so that takes care of what we're planning to do in terms of formal logic. The reason we wanted to cover the formal logic is as a background to something called proofwriting. Okay? So mathematical proofwriting is you essentially determining the truth value of some mathematical statement. So in terms of what we're looking at, we'll be looking at theorems. And remember, theorems were mathematical facts that were supposed to be true. Okay? So in terms of what it is, there's some sort of things they tell you, some information that the theorem tells you. You're supposed to have thing 1 and thing 2 and thing 3 all happen, and then you're supposed to get some conclusion. Now, if you want to actually prove that mathematical theorem, you could totally put this thing into a truth table if you wanted to. And it would simply be taking this implication where you've got a bunch of ands for the if statement and then some conclusion for your then statement, and you could throw it into a truth table. To be honest here, that is way more work than what we actually want to do. So we're actually not going to put it into a truth table. Instead, we're going to do something definitely related to and coming from the notions of the truth tables, but a little bit different. Okay. Now, if this first if part, so if the hypothesis is false, automatically the implication is correct or is considered true. But if your implication here is true, the thing we're actually going to be doing is just dealing with the first 2 rows of our truth table, and that is if this first if part is true, we want to verify that the conclusion, the Q part, the then part, is also going to be true. Okay, so that's the key thing that we're going to care about here. Okay, now in terms of the terminology that we just looked at a couple minutes ago, in terms of the truth table, this means that we're actually verifying that our theorems are in fact tautologies. Okay? Now, I think let's just stop at this point, and then next time we'll start off here, and then we'll start looking at how these guys could be written out, and they are typically written out in terms of sentences, and then we'll look to see what strategies we're going to be using instead of truth tables, although highly related to truth tables. Okay, so that we'll go ahead and end there, and that's everything for today. We were about one example before I was going to have us do activity 3, so we'll just do that towards the beginning of next time. Or if you've already worked through it, you're all set to go in terms of that as well. Okay? Just as a heads up on that. But I don't have anything else. I'll hang out for a few minutes if you guys have questions, but that's it for today.